So at this point, I'm going to move on to the third presentation by Mohammad Aghajani Delavar from Texas A&M University, College Station. And the title is Assessment of Gradient Inelastic Flexibility Based for Shear-Critical RC Members. Mohammad, please take it over.
Hi, everyone. Thank you for the introduction, Ali. And also, I want to thank my co-authors, Dr. Sideris, my advisor, and Dr. Salehi, who is a former graduate research assistant. In this presentation, I'm going to go through the assessment of gradient inelastic flexibility-based beam theory for shear-critical RC members, which then extended to generalized GI formulation. The outline of this presentation will be introduction, element formulation, concrete material model, assessment, ongoing research, summary and conclusion, and finally, any questions that you have. You know that the collapse of the structure is the worst phenomenon can occur. So predicting it will be so helpful and worthy. So can we predict it? Or is there any analytical model to do that? One of the models that can predict the softening part of the element reasonably is GI beam theory, gradient inelastic beam theory. It has some advantages over classical beam theory, like eliminating a strain localization phenomenon and providing response objectivity. Considering the flexural critical column as shown and applying vertical and lateral load to do pushover analysis, you can see that the local beam theory could not converge with increasing number of integration points. However, GI beam theory could converge with number of integration points, which represents the applicability of this theory for the post-peak response. However, the results you saw were reasonable for the flexure critical members. GI formulation cannot solve for the shear critical members because it was not extended to account for shear failure. This is the main restriction of this formulation up to now. Considering shear flexure critical column as shown in the figure, GI formulation could not follow the same pushover curve as the experimental one. So here is the question there. Can we extend the GI beam theory to capture shear failure? So this question is the main purpose of this presentation, which will be answered later. Now let's talk about the generalized GI beam theory, which is the extended GI beam theory considering shear and torsional deformations. The advantages that I want to show you are generating realistic shear strain distribution through higher order cross-section fields, that here we considered higher order kinematics to capture realistic shear strain distribution. As you may know, we have Euler-Bernoulli beam theory that considers plane section remains plane and normal of the section plane remains perpendicular to the axis of the beam. Timoshenko beam theory, in which plane section remains plane but not perpendicular to the neutral axis. And higher order beam theory, which none of those assumptions are valid anymore. So it considers general deformation in beam section, which will be a realistic one. Other advantages that I'm mentioning now will be covered later, like capturing the 3D stress-strain interactions in the concrete response through the 3D damage plasticity model, considering confinement effects by employing through the depth equilibrium over the cross-section, and preventing a strain localization through the definition of the GI formulation. Now we can go through the GI formulation, which has 4 sets of formulation as equilibrium, which has 6 functions in 3D space, section constitutive law, which relates section forces to section strains, non-locality relations, which relate the material section strains to macroscopic section strain, and you see that the characteristic length LC in the formulation, which controls the locally induced damage and presents the localization in the model, and the strain displacement equations, which relate the microscopic sectional strains to beam displacements, and also the boundary condition that we have considered as shown in the picture. Therefore, the analytical solution can be summarized as equilibrium that by having boundary conditions through the definition of the force shape function, which is d of x in the equation, we can find section forces. Then through the section constitutive law, by having the section forces from the last step, the material section strains can be computed. Then through the non-locality relations and having the material section strains, macroscopic section strains can be obtained. And finally, the displacements at the defined boundaries can be found through the strain displacement equation. So by substituting these equations, the overall analytical form has two general equations with two unknowns, as shown in the analytical form that can be condensed for the discretized form for implementing into the software that we use OpenSea. Here is the question that what is the difference between the generalized GI and original GI beam formulation? So as you saw, the approach was identical. However, inside the equations, there are some differences in section strains and the material constitutive law that make it to be generalized. So all changes are considered in section constitutive law. Now I want to mention the differences between generalized GI and GI beam theory. One of the differences is the cross-section kinematics, that instead of using linear cross-section kinematics in the generalized GI beam theory, we've considered third-order kinematics considering warping effects when non-circular cross-section is the case. The strain field can be computed by the derivative of the deformations and by applying the boundary conditions, which are zero shear stress at the beam lateral surfaces and traction-free of warping function. The strain field can be summarized as what you see here, these equations. And from the strain field, epsilon yy, epsilon zz, and gamma yz are zero, which is not true because we know about the Poisson effects and confinement effect in the RC element due to the stirrups. So what's the solution for that? How do we address that actually? So through the depth equilibrium over cross section is applied to capture these strains which are not obtaining through the cross section kinematics. The I that is mentioned here is represents the fibers. Now I'm gonna go through the next main difference of generalized GI with GI beam element, which is the concrete constitutive model. You can see the beer formulations used to define concrete material model, which is based on the Fenves material model. This model is actually an elastoplastic damage model. As you see, the strain is decomposed to elastic and plastic parts, and damage factor is coupled with classical plasticity theory. The yield, as you see here. And the yield surface is a loop-linear yield surface with the cohesion functions based on Barcelona model. And also, there is a plastic evolution and damage evolution to solve for the material. Here is the question that, what is the difference between this model and the Fenves material model? So, the main difference is we are handling the strain localization in element level. However, the Fenves model is considering material rescaling based on fracture energy concepts. For the numerical modeling approach of the mentioned concrete material model by providing material parameters, total strain, kappa, which is a cumulative damage parameter, and plastic strain, we can find effective stress through the definition. And by checking the yielding criteria, which the yielding criteria as mentioned before is the linear yield surface, we can see that if it's satisfied, we are in the elastic domain, and we can find the total stress. And if this yielding criteria is not checked, we are in the inelastic response. So we need to compute M and H, which M is the flow vector that represents the plasticity direction, and H is the plastic modulus. And then we can find other parameters to check the yielding criteria, and we try to satisfy the yielding criteria. After doing that, we can compute the total stress and saving the epsilon plastic and kappa for the next step. You can see from the figures that the material model response, even with a lot of complexity, is close enough to the experimental results. By implementing all the formulations in the OpenSeas and analyzing the shear flexure critical column of Gio-Martusian in 1998, you can see that the convergence by increasing the number of integration points can occur for the post-peak responses for shear critical member. And the macroscopic section of strain distribution along the column height is shown that the distribution is reasonable as maximum shear strain is occurred at the column ends, and the zero curvature is occurred in the middle of the column. The effect of the characteristic length, which is usually equal to the cross-section's depth on the response of the given column, is shown in the figure that by increasing the characteristic length, the post-peak length deterioration is delayed. And finally, the pushover curve of the proposed model is compared with the experimental results. And as you see, the model can capture the strength fairly well. Because the model did not account for bundle slip effects, the predicted response exhibits higher stiffness than the test data. And as an ongoing research that we are working right now is defining the separate damage in tension and compression that we can have more reasonable damage coefficient that you can see here. We can decompose sigma to sigma t, sigma in tension and sigma in compression. And in the next step, defining the effect of tensile strain on compressive damage and vice versa, which we will expect to predict better results in cyclic loading by defining beta TC and beta CT, which can be computed from the literature, and validating the model with other experiments on the general loading type. And in summary and conclusion, you saw that generalized gradient in elastic beam theory was proposed to account for shear flexural interactions in beams or columns of rectangular cross sections that have some benefits, like gradient inelastic formulation eliminates a strain localization phenomenon. Higher order cross section deformation field captures shear strain distribution. Through the depth equilibrium captures the confinement effects. And 3D damage plasticity concrete model captures the 3D stress strain interactions in the concrete response. And finally, we implemented the generalized GI beaming column formulation in the OpenSeas, and you saw that the simulation of a shear flexure critical RC column under monotonic lateral loading showed the capability of this element formulation to closely predict the column strength. Thank you. Any questions? I can answer it. Okay, I received question that how can the model identify the difference between flexure and shear deformation component? So as you saw in the formulation, you can see that. So actually we have both components in the formulation. Let me. So here in this formulation, the flexure deformation will be computed through the epsilon XX because of the tension and compression that the flexure can be applied. But for the shear one, we have gamma XY and gamma XZ really, which will be defined by the strains of the shear one, actually the shear strain. I don't know I can answer your question or not. Actually, the formulation is modified.
Okay, Mohammad, thank you.